Welcome to a deep dive into the foundational power behind every successful machine learning endeavor. Today, we're uncovering the indispensable role of statistics, not just as a supporting player, but as the very bedrock upon which intelligent systems are built. Without a robust understanding of statistical principles, machine learning becomes a series of educated guesses rather than a systematic approach to discovery and prediction. Before we even consider model architectures or complex algorithms, our journey begins with the data itself. Statistics provides the lens through which we truly understand our datasets. Descriptive statistics, like mean, median, mode, variance, and standard deviation, are our first tools. They illuminate the central tendencies, spread, and shape of our features, helping us identify outliers, understand distributions, and spot potential biases inherent in the raw information. Beyond simply describing data, inferential statistics allows us to draw meaningful conclusions about a larger population based on a sample. This is critical for feature selection, where we might use hypothesis testing to determine if a particular feature's relationship with our target variable is statistically significant, rather than just a random fluctuation. This ensures we're feeding our models truly informative inputs. The messy reality of raw data often requires significant preparation. Statistical insights guide critical preprocessing steps. Techniques like standardization and normalization, for instance, are rooted in statistical concepts to scale features appropriately, preventing dominance by variables with larger numerical ranges. Missing value imputation can also leverage statistical measures, filling gaps with mean, median, or more sophisticated model-based estimates. Choosing the right machine learning model is not arbitrary. It's deeply informed by statistical thinking. A core concept here is the bias-variance trade-off. Bias refers to a model's tendency to consistently learn the wrong thing by simplifying assumptions, while variance describes its sensitivity to fluctuations in the training data. Statistics provides the framework to understand and balance these competing forces to achieve optimal generalization. Furthermore, many machine learning models have underlying statistical assumptions. Linear regression, for instance, assumes a linear relationship between variables, normally distributed errors, and homoscedasticity. Violating these assumptions can lead to unreliable model performance and invalid inferences. A solid statistical background helps us recognize when these assumptions are met, or when alternative models are necessary. The process of training and validating models also relies heavily on statistical principles. We statistically split our data into training, validation, and test sets to ensure an unbiased evaluation of performance on unseen data. Cross-validation techniques, such as k-fold cross-validation, are statistical methods designed to provide more robust estimates of model performance and reduce the impact of data splitting choices. Once a model is trained, evaluating its performance demands statistical rigor. Metrics like accuracy, precision, recall, F1 score for classification, or mean squared error and R-squared for regression, are all statistical constructs. They quantify how well our model's predictions align with the actual outcomes, giving us objective measures of success or areas for improvement. Comparing multiple models or different configurations of the same model often requires statistical hypothesis testing. Instead of simply picking the model with the highest metric value, we can use statistical tests to determine if one model's performance is better than another's, rather than just trivially better due to random chance. This adds confidence to our model selection. Understanding overfitting and underfitting is also inherently statistical. Overfitting occurs when a model learns the training data too well, capturing noise and specific patterns that don't generalize. Underfitting, conversely, happens when a model is too simple to capture the underlying patterns. Statistical techniques like regularization, which penalize complex models, directly address these issues. Hyperparameter tuning, the process of optimizing a model's configuration settings, often involves statistical optimization techniques. Grid search, random search, or more advanced Bayesian optimization methods explore the parameter space, often guided by statistical models of how different parameters impact performance, aiming to find the statistically optimal configuration. Finally, the ultimate goal of machine learning is to inform decision-making. Here, statistics ensures our decisions are robust. Interpreting model outputs, understanding confidence intervals around predictions, and assessing the statistical significance of feature importances allow us to translate complex model results into actionable, reliable insights, rather than just black box predictions. Even in the realm of ethical AI, statistics plays a crucial role. Statistical analysis helps us detect and quantify bias in datasets and algorithmic outcomes. By examining disparities in model performance across different demographic groups, we can identify and work to mitigate unfairness, ensuring our machine learning systems are not only effective but also equitable and just. In conclusion, statistics is not merely a prerequisite for machine learning, it is its very language, its guiding philosophy. From understanding the raw data and selecting the right features, to choosing and evaluating models, tuning their parameters, and making reliable decisions, statistical thinking underpins every critical step. To truly unlock the power of machine learning, we must first embrace the foundational strength of statistics.